All right, for my third and final mathematical induction example, again, I'm doing a question involving a sequence versus a series. It's a little bit more complicated than the previous one because we're dealing with inequalities as opposed to equations. So it's a little bit more complicated. Anyway, let's start with part one, which is not induction. It says, state the third term A3 of the sequence. So we have our sequence defined here. You can see it's a recurrence relation because each term is equal to the square root of 2 plus the term before it. And of course, they gave us the first term, A1, as root 2. All right. So they want us to find A3. Now, because each term is based on the term before, in order to find A3, we need A2. And in order to find A2, we need A1, which we do have. So before we jump to A3, we're going to find A2, and then we'll find A3. So according to the definition, A2 is going to be equal to the square root of 2 plus A1. A1 is the term before A2. Now we know A1 is root 2. So we're going to plug that into our calculators and get 1.85. Or we can leave it exact. This would be the exact value. Right, so I think I'm going to go ahead and use the exact value for A3. So A3 is going to be equal to, according to the definition, the square root of 2 plus A2, which is 2 plus square root of 2 plus A2, we found to be this as an exact value. And again, we can plug it into our calculators and get the decimal value, which is, according to my calculator, 1.96. All right, so that takes care of part one. Now we get to the induction part. It says, use mathematical induction to prove that xn is increasing and that it is bounded above by 3. Now, when this question came, I think, or my thought was that this was supposed to have been an, not xn, right? So I think it's a typo. So we need to show that our sequence, the terms in our sequence, they're increasing, right? We also need to show that they're bounded by above by 3. That means they will never go beyond 3. Now, mathematically, or I should say symbolically, let me just erase these so I can see better. They have written for us what it is that we're to prove. So they gave us in words, but they gave us symbolically as well. They told us that we need to prove that an is less than an plus 1, right? That is for the increasing part, to show that the sequence is increasing. You're showing that a term is less than the term after it, right? If it's increasing, it means that the fifth term is going to be less than the sixth term, and so on, because the terms are increasing. In terms of the bounded above by 3, we need to show that an is less than or equal to 3. So the terms in our sequence will be less than or equal to 3. They're bounded by 3. Okay? Now, we're going to proceed just like we've done with all the other induction questions. We're going to do our base step. We're going to do our inductive hypothesis. And then we're going to do our inductive step. The inequality questions are a little bit more challenging than the equation ones but I'm going to show you my approach for these types of questions. We're going to start, just like I've started with the others, by defining my PN, my statement that I'm proving. I'm proving two things actually, that AN is less than AN plus 1 and that AN is less than or equal to 3. These two things. All right. We're going to start with our base step as usual. And remember, our base step is to prove that our statement is true for the smallest value of n. And it's clear here that the smallest value of n is 1. So we're proving that P1 is true. All right, so let's look at the AN less than AN plus 1. So it's not an equation, so we're not doing left side, right side. I'm just going to write this with my n plugged in as 1. So I'm going to have A1 less than A2. I'm going to put a little question mark. I don't know. I'm checking to see. So is A1 less than A2? Well, we know the value of A1, which is root 2. Is it less than or equal to A2, which is 1.85? According to my calculator, the square root of 2 is 1.41, which is less than 1.85. Right, so we were checking this piece of the statement. Is AN less than AN plus 1 with n plugged in as 1? So is A1 less than A2? I have a little question. I have my less than sign and a little question there. And then I have A1, which is given as root 2. Is it less than the 1.85 we had gotten for A2? Well, root 2 is 1.41, which we know is less than 1.85. So this part of the statement is true. Let's look at this part now. So I'm working each of them. So A1 less than or equal to 3. Is that true? So I have a little question mark there. Well, A1 is root 2, which is 1.41. And 1.41 is less than or equal to 3. So I can say, therefore, P1 is true. I have proved my base step. I'm going to switch slides and move on to my inductive step now. Or rather, my inductive hypothesis. And remember that this is the assumption part, which is assuming that PK is true. I'm going to write down what that is. We are assuming, if we look back, we're assuming, so we're taking our PN statement now, and wherever there's an N, we're plugging in K. So we're assuming that AK is less than AK plus 1. And we're assuming that AK is less than or equal to 3. Good. So that is our assumption. And then final step, our inductive step, we're going to prove PK plus 1 is true. That is, going back to our statement, wherever there's an N, this time we're putting K plus 1. So K plus 1 here, K plus 1 there, K plus 1 there. So we're going to have AK plus 1 is less than AK plus 1 plus 1, which is K plus 2. And AK plus 1 is less than or equal to 3. That is what we want to show. Now, when we were doing the equations, we would start with, for example, one side of the equation and use our assumption and get or arrive at what it is that we're trying to prove. With the inequalities, I do it a little bit different. I find it's easier to start with the assumption and then build on it using the definition of the sequence until we get to here. Right, so I'm not going to be taking one side of this and working it. I'm going to be starting from my assumption and then manipulating it in such a way based on the definition until I arrive at this, right? I find that way to be easier. So I'm going to say from my assumption, I'm just going to write my assumption again. Good. Now I am going to, because I want what's on the left side of this inequality to be AK plus 1. So currently I have AK. What I want is AK plus 1. So I need to see the connection. I need to look at the definition of the sequence to see the connection between AK and AK plus 1. Let's look. So this is our definition here. That's the definition. So according to this definition, AK plus 1 would be equal to the square root of 2 plus AK, according to the definition, right? So to move from AK to AK plus 1, I need to take the AK, I need to add 2 to it, and then I need to square root it, right? Because my aim, let me show you again. On the left side of my inequality for the assumption, I have AK, but I need to manipulate this AK so that it becomes AK plus 1. To do that, I use my definition. Let's go back to the definition. According to the definition, AK plus 1 is equal to the square root of 2 plus AK. So to move from AK to AK plus 1, I need to add 2 to the AK and then take the square root of that. So I'm going to add 2 over here on the left side. But of course, if you add 2 on the left side, you have to balance it by adding 2 on the right side of the inequality as well. So I'm going to add 2 there. Good. And then I'm going to take the square root. Now I'm dealing with positive terms that are increasing from 1.4. So I'm allowed to take the positive square root, right, without thinking about changing the inequality. So take the square root of both sides. Now what I have on the left side now, according to the definition, is AK plus 1, because AK plus 1 is the square root of 2 plus AK, which is exactly what I have here, the square root of 2 plus AK. So this is actually, I've manipulated this to get AK plus 1. And what is this? Look at the right side now. I have 2 plus AK plus 1 square root. You look back at the definition. Remember, the definition is saying, if you have a term, you add 2 to it and you take the square root, it gives you the next term, the term after the AK, right? So if you have a term, add 2 to it and take the square root, it gives you the next term. That's exactly what I have here. I have AK plus 1, add 2 to it, take the square root, which means this gives me the next term, the term after the AK plus 1 term, which would be the AK plus 2 term. And look at that. I have arrived at piece of where I need to go. I have piece of it. I haven't done the and part yet, but at least this part is done. For this piece now, similarly, I'm going to start from the, I think I have an arrow. My AN should have been replaced with AK plus 1, not K plus 2. So I have an arrow right here. Right? So it's actually, because I had replaced, wherever there was an N in my statement, I replaced it with K plus 1. So this should have been K plus 1. Okay. All right. So in order to prove this, I'm starting from here. I'm starting from the assumption, right? And I'm going to build on this again until I get AK plus 1, doing the same thing I did before, adding 2 and taking the square root and ensuring I do it on the other side as well. So I'm going to add 2 on both sides. And then take the square root. The left side, what does it give me? You should be saying AK plus 1, right? You have a term, you add 2 to it and take the square root. It gives you the next term. So this is AK plus 1, less than or equal to the square root of 5. Now the square root of 5 is 2.24. Some of you might be panicking at this stage saying you didn't get the 3. Well, guess what? If the term is less than or equal to 2.24, by the transitive property, it must also be less than or equal to 3. Right? There's no way it could be less than 2.24 and not less than or equal to 3. So we can go ahead and just say it is less than or equal to 3. So we've proven both statements, right? This piece and this. Therefore, PK plus 1 is true. And then, of course, I'm just going to put it over here. We would continue with our statement, our final statement. Since P1 is true and PK plus 1 is true, assuming PK is true, then by the principle of mathematical induction, our Pn is true.